find the equivalent capacitance. Find the equivalent capacitance of the given group of capacitors. Of the given group of capacitors. Connected in parallel. Connected in parallel. And we have these capacitors here. So this one would be capacitor 1, capacitor 2, capacitor 3, and capacitor 4. The capacitance of the capacitor 1 would be 2 microfarads. The capacitance of capacitor 2 would be 3 microfarads. The capacitance of the capacitor 3 would be 5 microfarads. And the capacitance of the capacitor 4 would be 3 microfarads. So what we have here, we have a parallel connection. So we have a parallel connection. We know that the equivalent capacitance of a parallel connection is the sum of the individual capacitance of each capacitor. So it's C1 plus C2 plus C3 plus C4. So equivalent capacitance in this case will be 2 microfarads plus 3 microfarads plus 5 microfarads plus 3 microfarads. So adding 2 plus 3, 5, plus 5 is 10, plus 3, 13 microfarads. So what is the equivalent capacitance in this case? The equivalent capacitance is, in this case, 13 microfarads. Let us see now one example when we connect those same capacitors now in series. When we connect those same capacitors in series. May I change the type? Yeah? Did you finish the copy? Well, now look at this. They say find the equivalent capacitance. Find the equivalent capacitance of the given group of capacitors, of the given group of capacitors connected in parallel. Connected in parallel. And then the connection we have is like this. So this will be the capacitor 1, capacitor 2, capacitor 3, and capacitor 4. And capacitor 1, we have a capacitance of 2 microfarads. Capacitor 2 to be 3 microfarads. Capacitor 3, 5 microfarads. Capacitor 3, 5 microfarads. And then the capacitor 4 will be also equal to 3 microfarads. Now, when the connection of the capacitors is in parallel, then we know that the reciprocal of the equivalent capacitance will be equal to 1 over the capacitance of the capacitor 1 plus 1 over the capacitance of the capacitor 2 plus 1 over the capacitance of the capacitor 3 plus 1 over the capacitance of the capacitor 4. If now I substitute the capacitance of these 4 capacitors by their values, we get that 1 over the equivalent capacitance is 1 over 2 microfarads plus 1 over 3 microfarads plus 1 over 5 microfarads plus 1 over 3 microfarads. And then now, let's go over our knowledge of algebra. What is the least common denominator? Least common denominator among the values 2, 3, or 1 over 2, 1 over 3, 1 over 5, and 1 over 3. What is the least common denominator? The least common denominator between all those numbers is 30. So 30 is the smallest number divisible, by all those denominators. So if I want to combine all those fractions, if I want to add all those fractions, I have to have the same denominator. And that least common denominator here would be 30. So we say this: if I know that my LCD is 30 and I have 2, I need to multiply these 2 times 15 to get 30, right? But if I multiply below by 15, I have to multiply also above by 15. So we multiply my third fraction by 15 over 15. Now, I want to get 30. I have 3. So we multiply this one by 10. And then we multiply above times 10 also. I want to get 30. So we multiply this one times 6. Because 6 times 5 is 30. And I will multiply above times 6 also. And then I will multiply this one times 10. Because like that, I get 30. And I will multiply the numerator times 10 also. So now we say that 1 over the equivalent capacitance is 15 over 30 microfarads plus 10 over 30 microfarads plus 6 over 30 microfarads plus 10 over 30 microfarads. I have the same denominator, 30 microfarads, in all my fractions. So I can add the numerators, keeping the same denominator 30. So 1 over the equivalent capacitance would be common denominator 30 microfarads. I get 15 plus 10 plus 6 plus 10. This is equal to 41 over 30 microfarads. So if you have that 1 over the equivalent capacitance is 41 over 30 microfarads, if you want to get the equivalent capacitance, you flip both fractions. So by flipping 1 over the equivalent capacitance, you get equivalent capacitance. And flipping 41 over 30 microfarads, you get 30 microfarads over 41. So when you divide 30 by 41, you get that the equivalent capacitance is going to be 0.37 microfarads. And there you have now the equivalent capacitance of these 4 capacitors connected in series. Sorry, come on, I said there is an error here, right? In the statement of the problem, sorry. And the error is that it had to say here series, not parallel, right? Because this connection is in series. There was an error here in the statement of the problem. This is series connection, not parallel connection. Parallel connection was the previous one. So these are 2 examples about calculating the equivalent capacitance. Now, we could have one case where you have a combination of both connections, series and parallel, right? So how do you work when you have a combination of 2 connections, series and parallel? So some of the capacitors are in parallel and the other capacitors are in series. So how do you work with that combination? May I erase? Look at this now. Oh, come on. They say 2 capacitors of 4 microfarads each are connected in parallel. And then a third capacitor of 6 microfarads is connected in series with the first 2. Is connected in series with the first 2. So they say here, what is the capacitance of this combination? What is the capacitance of this combination? So what they use? They give us a combination that will look like this. So we have here a capacitor of 6.0 microfarads. And then here you have the two capacitors of 4.0 microfarads. Let's call this capacitor capacitor 1. Let's call this capacitor capacitor 2. And let's say that this capacitor is the capacitor 3. So capacitor 1 and capacitor 2 in this case are in parallel. And if they are in parallel, the equivalent capacitance is the capacitance of the capacitor 1 plus the capacitance of the capacitor 2. So it's 4.0 microfarads plus 4.0 microfarads. So the equivalent capacitance of these two capacitors is 8.0 microfarads. That means that now you can reduce this to two capacitors, one of 6.0 microfarads, that is the capacitor 3, and another one of 8.0 microfarads, that is the capacitor equivalent of the parallel connection. I will put a P of parallel to identify that this is the parallel connection. But now, these two capacitors, C equivalent in parallel and the capacitor 3 are in series now. So the capacitance equivalent in series would be 1 over equivalent capacitance in series would be 1 over equivalent capacitance in series is 1 over equivalent the capacitance of the capacitor 3 plus 1 over the equivalent capacitance in parallel. So 1 over this equivalent capacitance in series is 1 over 6 microfarads plus 1 over 8 microfarads. Between 6 and 8, the least common denominator is 24, right? So I can multiply these 6 times 4 and above here times 4, and I can multiply the 8 times 3 and this above here times 3. Because like that, I will get 24 in both denominators. So I can say now that 1 over the equivalent capacitance of the series capacitors is 4 over 24.0 microfarads plus 1 times 3, 3 over 24.0 microfarads. So now, adding the numerators, we get 1 over the equivalent capacitance in series is equals to 4 plus 3, 7 over 24.0 microfarads. Now, if I flip both sides, I will get that the equivalent capacitance in series is 24.0 microfarads divided by 7. So the equivalent capacitance in series will be, if you divide 24.0 by 7, you will get 3.43 microfarads. So the result in this case is 3.43 microfarads. Now, let's see some exercise now about the capacitance of the capacitor. So calculating the capacitance of the capacitor and calculating the energy in capacitor. So may I raise? Look at this one. They say an ideal air-filled parallel plate capacitor with a plate separation of 4 centimeters, with a plate separation of 4.0 centimeters, has a plate area of 0.040 meters squared. What is the capacitance? What is the capacitance of this capacitor with air between these plates? With air between these plates. And they give us the permittivity of the free space constant, epsilon sub 0. They say there is 8.85 times 10 to the negative 12 Coulomb square over Newton meter squared. So what we know the plate separation and we know the plate area. We know the permittivity of free space, but we don't know the capacitance. So this is a very simple calculation. So the only problem here is that the distance between plates is given in centimeters. And I need to work in meters. So I know that 1 meter have 100 centimeters. Like that, you cancel the centimeters out. Centimeters. Like that, you cancel the centimeters out. And then you divide 4 by 100, and that gives you the distance in meters. That is going to be 0.04 meters. So the distance in meters is 0.04 meters. So you have to convert. Why do you have to convert the distance given in centimeters into meters? Because look at the unit of the permittivity of free space. This constant has its units in meters. So you need meters here, and you need meters in the area. If they don't give you meters squared, you have to convert to meters squared that area, because you need meters everywhere to calculate that capacitance. Now, what do we know? We know that the capacitance is the permittivity of free space times the area divided by the distance. So we know that the capacitance would be 8.85 times 10 to the negative 12 coulombs squared over Newton meter squared times the area now 0.04 meters squared divided by the distance between plates, there is 0.04 meters. That means that now when we calculate the capacitance, these meters squared, so this meter here cancel with one of the meters, right? But at the end, we're gonna get again meters squared below. Sorry, we have meters squared. I'm sorry. We have meters squared here, and they will cancel with this meters squared. At the end, you will get coulombs over Newton meter, and that will be the farad. So when you divide these numbers, 0.04 over 0.04, it will be 1. So you get 8.85 times 10 to the negative 12 farads. 10 to the negative 12 farad is 1 picofarad. They are using two significant figures only here. So I will express my answer with two significant figures. So this will be approximately 8.9 picofarad, because 10 to the negative 12 farad is 1 picofarad. So the answer in this case is 8.9 picofarads. 8.9 picofarads. Now, let's see one example with a dielectric. Let's see one example containing a dielectric. So, may I erase this? Okay, look at the next example. They say in the next one, a parallel plate capacitor with plate separation of 4 centimeters. With plate separation of 4.0 centimeters. Has a plate area of 6.0 times 10 to the negative 2 meters squared. So they say, what is the capacitance of this capacitor? What is the capacitance of this capacitor? If a dielectric material with dielectric constant of 2.4 is placed between the plates. comma, completely filling the space. Completely filling the space. And again, they use the permittivity of free space. They say there is 8.85 times 10 to the negative 12. They say there is 8.85 times 10 to the negative 12 coulombs squared over Newton meter squared. Now, again, we have the distance between plates in centimeters. So we know that 4.0 centimeters times 1 meter every 100 centimeters, it will give us 0.04 meters of distance between plates. Now, the capacitance now include, and the capacitor include a dielectric material between plates. Then now the capacitor, the formula of the capacitance, include a constant K. So we say K times epsilon sub 0, then the area over the distance between plates. So what is going to be your capacitance? You have your dielectric constant of 2.4 times the permittivity of free space, 8.85 times 10 to the negative 12 coulombs squared over newtons meter squared. The area, that is 6.0 times 10 to the negative 2 meters squared, divided by the distance, that is 0.04 meters. So these meters squared are going to cancel out with these meters squared over here. And then now when you calculate the capacitance, you will get that doing all these pros and divisions, you get 3,186 times 10 to the negative 14 farads. Then I will move the decimal point 2 places to the left to get 10 to the negative 12, because like that I get pico. So we say that this is the same that 31.9 times 10 to the negative 12 picofarad, which is approximately, with two significant figures, 32. Sorry, there is no 10 to the negative 2 here. I don't know why I'd say 10 to the negative. This is 31.9 times 10 to the negative 12 farads, still in farads. And then this is 1 picofarad. So this is 31.9 with two significant figures, would be 32 picofarad. And that is the capacitance. So this is 31.9, so 32 times 10 to the negative 12 farad, which is 32 picofarads. Remember that 10 to the negative 12 is the prefix pico. Just only one more thing. Look at this other side that I will show you now. That is, if I know the capacitance of a capacitor and I know the difference in voltage between the plates, how can I find, the charge of the plates? How can I find how can I calculate the charge on the plates? So let's see then the next and last exercise. And in this one, they say, what charge accumulates on the plates of a 2.0 microfarad air-filled capacitor. Air-filled capacitor. When it's charged until the potential difference across its plates across its plates is 100 volts. Now, what we know, by definition, we know that capacitance is the ratio between the charge on the plates and the variation of voltage, difference of voltage between those plates. Now, if I want to find, the charge that accumulates on the plates, what you want to find is Q. Q is the charge that is accumulates in the plates. So you can say that Q is equal to, you multiply times V both sides, C times V. You can say that Q is equal to, you multiply times V both sides, C times V. Now, see, the capacitance is given in microfarad. So 2.0 microfarad is the same that 2.0 times 10 to the negative 6 farads, because 1 microfarad is 10 to the negative 6 farad. So I can say that Q is 2.0 times 10 to the negative 6 farads times the voltage, that is 100 volts. So Q, the charge, would be 200 times 10 to the negative 6 coulombs, and then 10 to the negative 6 coulombs would be microcoulomb. So 10 to the negative 6 coulomb is what is 1 microcoulomb. So you can say that this is 200 microcoulombs. So your answer, what amount of charge will be accumulated there? 200 microcoulombs.